These 4 methods that I'm going to teach you, they may not be the worst or the best, but you got to respect my honesty. I'm just going to teach you, and it might break your heart, but that's all I'm going to do, teach you and leave you. Okay?
Now I may not be the worst or the best, but you gotta respect my honesty. And I may break your heart, but I don't really think there's anybody as bomb as me. So you can
Salute. I don't think there's any other 4 methods as bomb as these. Alright. So the rewrite is a new one for us. Let's start off from the top. Usually when you start off with a problem, one thing you always want to try and see if it's just a plain one where everything's nice and the functions continues, and you could just do the plug-in method and go from there. In this case, if you plug it in, you get 3 times infinity plus 5 all over 6 times infinity plus 1, which quickly becomes infinity over infinity. You say, whoa, 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 outsides. Can't do that. That's an indeterminate form, and so you quickly say, you know what, the plug-in method failed, and what we're here today doing is learning a new method called the rewrite method. The rewrite involves amazingly just rewriting the expression algebraically. What you want to do is you're going to say, you know what, I wonder what we could do to get rid of the problem. The problem is that you're getting infinity over infinity. Often the cure for that is to rewrite it algebraically to where whatever the problem is, you've gotten rid of. So here the problem is that you got infinity, infinity. We could divide that out if we do multiplication on top and the bottom by 1 over x. So I'm going to multiply that by 1 over x and that by 1 over x, which is a legal step. All I'm doing algebraically, all I'm doing is multiplying by quantity that's equivalent to 1 most of the time. So that would give me a limit as x goes towards infinity of 1 over x times 3x plus 5 all over 1 over x times 6x plus 1, and that's just called a rewrite. And a little more algebra would yield this is the limit as x goes towards infinity of 3 plus 5 over x all over 6 plus 1 over x. Now once you've done the rewrite, if you've done something good here, which doesn't always happen, but if you have done something good, once you're done with that, you could start all over with the plug-in method and see how it goes. At that point, you try the plug-in method, and that would give you 3 plus 5 over infinity all over 6 plus 1 over infinity. Plug in infinity for x and infinity for x there. The 5 over infinity is 5 over a large number. That's undoubtedly going to 0. Same thing for this. And so you're getting 3 plus 0 and 6 plus 0, which gives you a grand total of 3 over 6 or 1/2, and that's the limit. Told you. I'm just going to teach you these 4 methods and leave you. Sorry if that breaks your heart, but that's all I'm going to do today. Let's try the plug-in method again. This one you try the plug-in method and you get infinity, infinity, and you say, whoa, 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 time out. Outsides, can't do this, you got to try something else. And so today we're practicing our brand new method, the rewrite. And in this case, it would involve finding out what is the dominating term on the top. You scan through it, degree 0. You know, for large x's, this is not that much. For large x's, this is okay. For large x's, this one dominates the top. We call this the dominating term because it's degree 2. You know, if this is a large number, x squared is so much more bigger than 3x. This becomes insignificant. On the bottom, the dominating term is obviously the 6x squared. So the degree 2 is the dominating term. So you'd want to do a little rewrite on this one. We're going to do a little rewrite and rewrite the limit as x goes towards infinity. Here's what we're going to do. We want to multiply top by 1 over x squared and also the bottom by 1 over x squared. Okay, then redoing the algebra, that would give you pi over x squared plus 3 over x plus 5 all over 6 plus 1 over x squared. I'm distributing that to every single term in there. And then you do a little more cleanup. You do the plug-in method now and see how that goes. Everywhere I see x, I'm going to do infinity. So this will give me pi over infinity squared, which is infinity, plus 3, which is 0. Well, infinity squared would be infinity. 3 over infinity plus 5, 6 plus 1 over infinity squared. You scan through that and you try to compute little pieces that you know for sure are computable. pi divided by a huge number, that's going to be 0. 3 divided by a huge number, that's going to be 0. Everything here seems computable without much controversy. I don't see anything here that would be indeterminate, and I get the total of 5 on the top, 6 out on the bottom for 5, 6. So there you go, the rewrite method succeeding where the plug-in method failed, and actually avoiding the engineer's method altogether, giving you a third option. So far we've got 3. The plug-in method, but when it gives you indeterminate forms, you can go to the engineer's method, or this really nice stuff, the rewrite method. Very, very nice. But I'm just going to teach you 4 things and then leave you, okay? Let's try it again. You just want to try it again? This one's a little bit different. This one, the top is degree 2 and the bottom is degree 3. And so, again, if you try the plug-in method, you get infinity over infinity, so you got to try something else. So you do the rewrite. And so you do the rewrite, and then you scan the top and the bottom. See, the other ones were different. The other ones, the top was degree 2, the bottom was degree 2, so it was pretty obvious. Well, after you do a few of these exercises, hopefully by the time you watch this, I will have a lot of homework problems posted. I'm really looking forward to writing up a nice homework set for this section, especially, actually for all of them, but we've only got 2 hands. I wish I had 8, like an octopus. But anyways, soon you'll have a homework set where you try a lot of these. And after you get to try a lot of these, you get the hang of it. If this is degree 2, well, the obvious thing is kill the degree 2 by dividing it from top. This one poses a little bit slightly different challenges. These are different degrees. So should you divide by x squared or x to the third? The truth is that sometimes either one will get the job done. So don't be afraid to experiment. You can only fail if you don't try. I'm going to slap a 1 over x squared on both of them, and that will rewrite it to become the limit as x goes towards infinity of 2 over x squared plus 3 all over 6x plus 1 over x squared. Then I'm going to try my plug-in idea again. Everywhere I see that, so that gives me 2 over infinity squared plus 3. By the way, I don't really need the square because infinity times infinity would be infinity. So if I often write infinity here, that's because infinity squared is equal to infinity. So that would give me 6 times infinity plus 1 over infinity, like that. You see that? So this is going towards 0. That's going towards 0. That's going towards 0. In the end, what I see here, what do you guys see? Tell me what you see. I see 3 on the top, and I see infinity on the bottom. Is that what you guys see? That's what you should see. And now I have 3 over a large number, and then you ask, is that outsized? Is that indeterminate? No, that's clearly, I know what's happening. 3 divided by a large number, it's in the 0 bucket, right there, 0 bucket. And so again, the rewrite method succeeding where the plug-in method fails just by dividing it out. Okay, that's the one we just did. That was the screen I was looking for earlier. Too late. All right, how about this one right here? This was a nice, delicious problem we tried before with the engineer's method. Remember? You remember? This one is, you can also do, this one's really, really nice because we will get a chance to explain a lot of different ideas. Let's start off from the top. I'm going to make this really, really small because I need more space. Maybe that big. All right, so you first, of course, again, you first try your plug-in method, plug-in method, and that gives you infinity minus infinity. You say, whoa, outside it's violation. So you try something else, and we're trying the rewrite today. So the rewrite would be, let me just do it here because I already made the screen small. The rewrite would go something like this. The rewrite involves a famous idea from a long, long time ago. Let me do it here. Clear this page. Let me remind you of a famous idea from algebra. You remember when you had 3 over 4 minus the square root of 2, and your teacher always told you, hey, you got to rationalize the denominator. You multiply top and bottom by the conjugate on the bottom. You guys remember that? This is a famous idea. This was the idea of conjugates. Conjugates save the day. You look at the bottom here and you pick the conjugate and you do top and bottom by the conjugate. And you didn't just do it then, you also did it with complex numbers. If you have 5 over 3 plus I, and you needed to write it in standard form, you would multiply top and bottom by the conjugate. In this case, it would be 3 minus I. 3 minus I. So again, the conjugates, and you probably did it in trig too. Suppose you had something like 1 minus sine x, and you had to simplify that for some reason. You'd multiply it by 1 plus sine x over 1 plus sine x, and nice things would happen. On the bottom, you'd get a famous identity, etc. The idea of conjugates is super famous. It's pervasive everywhere. So it's a good tool to have available at your disposal anytime you want it. That's what we're going to try on this one. Are you guys afraid? I'm not afraid. So and I'm going to go with yellow, because yellow's mellow. X minus the square root of x squared plus 5x plus 21. I'm going to take this guy and multiply top and bottom by the conjugate, and the conjugate would be x plus the square root of x squared plus 5x plus 21 all over x plus the square root of x squared plus 5x plus 21. Yeah? And then see how it goes. And of course, you still got the limit here as x goes towards infinity. And of course, this is a rewrite, powerful rewrite. That would give you the limit as x goes towards infinity. Switch back to mellow yellow. On the top, this looks like the difference of squares, so it would look like x squared minus x squared plus 5x plus 21 all over x plus the square root of x squared plus 5x plus 21. You say, whoa, well, we made it into a mess, but just relax. You're in good hands. And so you clean it up here. That gives you negative 5x minus 21 on the numerator. That still gives you x plus the square root of x squared plus 5x plus 21. And then you could try your plug-in method again, and the plug-in method would give you, negative infinity over infinity, which is still indeterminate. By the way, the negative part shouldn't concern you. You could just leave that out of it. Worry about the actual numbers, and then you can figure that out and then put the negative back in there. So that negativeness shouldn't bother you. That doesn't make it or that doesn't change the indeterminateness of it. So, well, you say, well, that was useless. No, not really. There's more. But wait, there's more. But I'm just going to teach you this method and then leave you, okay? No, I'm going to teach you a total of 4 methods. And then that's it. I'm not going to evade it. That's all I'm going to do. So, alright, so then what you got to do here, you still have infinity, so you got to get rid of the problem. The problem is this number is really large. How could it not be large? Well, if you got rid of the x, that would stop it from being large. So one natural possible temptation may be to multiply top and bottom by 1 over x, and in fact, I'm not afraid I will do that. That would give me the limit as x goes towards infinity. On the numerator, that would give me negative 5 minus 21 over x all over 1 plus 1 over x times the square root of x squared plus 5x plus 21. Yes? So, whoa, this is kind of crazy. But no worries. Let me take a moment just to see what we got to do with that, because that seems like a little bit of challenge here, maybe to simplify. So let me take a different page here. Let's clean this up. If you have 1 over x times the square root of x squared plus 5x plus 21, and you wanted to simplify that, one way to look at it is to say, hey, maybe somebody unsimplified it for us. You guys remember when you have stuff inside the radical and you take it out, you take the square root of it or something? How would you do the backwards thing? Put it in there so it would kill that x squared. One option would be to change this back into a radical. The way you could say, well, maybe it came from this one, especially if x is positive, then this one is the same as that one. X squared plus 5x plus 21. And now this has the advantage that when you have 2 square roots, like this square root of a, square root of b, you can join them into a times b, right? You remember, right? You remember, oh shoot, I think you can't see that. Well, I'll put it over here. Square root of a times square root of b is equal to the square root of ab. I told you. If a and b are positive, you can always play that game. And since x is going towards infinity, positive infinity, it is positive. So So I can play that game. Now I can join them together and say, well, this would be 1 radical 1 over x squared times x squared plus 5x plus 21. And now I can distribute that to give me the 1 plus 5 over x plus 21 over x squared. Nice, huh? That is one way to simplify this. This has nothing to do with calculus. It's just algebra on a calculus problem here. So this becomes the limit as x goes towards infinity of negative 5 minus 21 over x all over 1 plus the square root of 1 plus 5 over x plus 21 over x squared. This I got from the other page, okay? From this page. Now I could try my plug-in idea here again. I'm not afraid. Plug-in method, and that would give me, let's see what that would give me. That would give me negative 5 plus 0 plus 21 over infinity over 1 plus square root of 1 plus 0 plus 0. Whoa, 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 whoa. Can you guys see that? If you cannot see it, I will slide it over. How's that? See it? So that would give me negative 5 over square root of 1 plus 0, 0. That's 2 on the bottom. So that would be a grand total of negative 5 over 2, which is equal to negative 2.5. Voila. Told you. So, that, my friends, that's the plug-in method. Or no, that's the rewrite method. Several ways. You divide out, use the idea of conjugates, a lot of different things. Plug-in rewrite method. Then, let's see. Oh yeah, let's do this one, plug-in method. So you plug in here, x goes towards infinity, you get infinity over infinity. You know, ln of infinity, which is also a large number, so you get infinity over infinity. You say, well, that's an indeterminate. So then what? Then you try to rewrite. The plug-in method fails, so you try to rewrite, and so you try to rewrite, and you try to rewrite, and you try to rewrite, and nothing comes to mind, man. We're out of ideas. You could play with it, but you can maybe go like this: 1 over x ln x, but that still gives you a problem. That would give you something like 0 times infinity. Yeah, this shows the problem here. You're invited to try to rewrite this into something that would turn into something better, but the point of this example being here right now is to point out the fact that the rewrite sometimes also fails. Why? Because it's hard to rewrite in a way that is helpful. So the moral of the story is that not all functions are easy to rewrite in a way that's helpful, which shows the limitations of the rewrite method. Okay, that's the rewrite method for you. A good little introduction. Of course, the rest of it is up to you. You got to practice all this stuff about conjugates and whatnot. There's a lot more work to do on your part, so hopefully we'll have the homework set ready for you soon, and you can get to it. All right, should we go on? Our fourth method, because I'm only going to teach you 4 methods, and that's it. I'm going to leave you. Just 4 methods. The graphing method. The graphing method is really very, very easy to do, very intuitive. It's a lot like the engineer's method. Let's have a look. So here's the fourth method, the graphing method. So suppose you wanted to find the limit of 1 over x as x goes towards infinity. I know we could do the plug-in method. If you did the plug-in method, you would just get 1 over infinity, and you get that's equal to 0, and you'd be done. That's not the point. The point is I'm trying to practice a new method. We're trying to do the fourth method here. So we'll put that aside for now and try to look at this way of looking at life. The graphing method is especially attractive when you've got a famous function like this and you know the famous graph for it. This is 1 over x. This is pretty famous. You've done it probably many times. It has these 2 little hills like this, and the idea for graphing is say, hey, you know what? These limits are best predictions of the y value. So you start here along the graph. Here's your x's, and your x's have to be going towards infinity. They're going towards infinity, and and your x's keep going towards infinity, and you've got to predict the y value as that happens. Right? So it's pretty easy. You know, here the y value is maybe whatever, you know, 10. Here maybe the y value is 5. Here maybe the y value is 2, etc., etc. So as you move on, is there a best prediction? Which bucket is it going to land in? That's what you want to do. That's what you want to predict. And so I thought we could use this little stick person to start doing the walking. And so we start off there, right? And maybe x is here. This is x, and this is y. Maybe y is, say, 10 or whatever. So then you move over a little bit. Move this way. So your x's are moving towards infinity. They're moving. Now your y's are right here. Now the y has gone down. And of course you move it some more. And now your y has gone down here. Look at the y's. They keep going down, down, down. As your x's move that way and that way. Let's move all the way. Let's move our x's all the way over here. And so move, 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 move this way, and your x's and your y's keep going down, down, down. So the more you move this way, you're trying to predict. Whoa, not that. Whoops. Move along the graph, along the graph, along the graph, and here you're looking at the y value along the graph as you move, 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 move along the graph. And so it's clear to see if just from the graph then that you've got a horizontal asymptote on the x-axis, and so the best prediction for this one is clearly, undoubtedly 0. That's the graphing method. It's so simple. Yet it's very, very powerful especially for famous functions. I mean, if it's not famous, then well, we'll talk about those before or later. Take a look at this one. This is a y minus f of x equals 3 minus 5 over x. So if you do the graph, it looks more or less like this. Again, you can imagine a person walking on the graph. The person walking on the graph. See a person walking on the graph. You're looking at the y. What's the y doing as a person is moving? Look at the y, look at the y, look at the y. The y value. This is what you're trying to predict, this one right here. The y value as the x's move. As the x's move towards infinity, you're trying to predict the y value. Okay? And you don't have to think that much here. You got a horizontal asymptote. The best prediction for the y value is 3. And so that's the graphing method. Again, a famous one, the arctangent function. By the way, when you do these famous ones in class, if you ever need to actually do some computation, just keep in mind that most people, once you're at this level, they always work with radians on these functions. So if you're graphing or whatever you're doing, make sure you're in radians. Let's put this stick person here walking as x goes towards infinity. As x goes towards infinity, here's your person walking, and you're looking at the y value. The y value is getting bigger and bigger and bigger and bigger and bigger, and it has an asymptote here at the famous point, of course, pi over 2. And so the more you walk on this graph, the more you ride it along towards positive infinity, the closer and closer and closer that gets to pi over 2. Look at that. I told you. I'll do it again. I told you. Didn't I tell you? It's going towards pi over 2. And so often that is a good way to approach it. If you have absolutely no clue what you're doing, this might be a good way to do it. If you can get to the graph, then it's a huge step in your favor. Okay, here's another reason why the graphing method is powerful. Look at this one. If you have the famous sine graph, you try to predict it as your x's move towards infinity. Look at the y's. Look at the y's. They go down and up and down and up and down and up and down and up and down and up. If you had to predict where they're going to, look at that. Try to predict where that line's going to go as you move it this way. It's kind of hard because it goes between 1 and -1 and all the values in between. It goes all over the place. So the best prediction for the y value as you move further and further to the right is that there is no best prediction. That's your best prediction. The limit does not exist. And this is a nice problem because it's our very, very first example where we show that everything is not nice all the time. There are cases where you've got strange things happening and there's no best prediction. And it's very, very easy to see on this graph. You know, There's no way to, you can't say it's going towards 0 because it gets out of the 0 bucket immediately. You can't say it's going towards 1 because it immediately gets out of the 1 bucket and starts going towards the -1 bucket. There's no bucket that is going towards. It's just jumping all the way around all the time, forever. And so this is a famous example of a limit that does not exist in our very, very first one, and it's clear to see from the graph. So 1 point for the graphing method. Of course, the drawback is that, even if sometimes you don't, this is not a famous graph, perhaps. So how are you going to graph that? You're probably going to graph that if it's not a famous one for you, either use a calculator or you're probably going to start plotting points. But if you're going to start plotting points, well, you might as well just do the engineer's method. You'd be plotting points here and trying to figure out what it's going towards. So the graphing method is often not that helpful if the graph is not something famous. If the graph is not famous, you're really just plotting points, or you're really just doing the engineer's method. It shows the resemblance between the graphing method and the engineer's method also, by the way. And even if you did know the graph, sometimes it's not that accurate. How do you know where it's going towards? Well, maybe you know that it's going towards approximately 7, but still it's not that accurate. Maybe it's 7.1 or something like that. So it's still not as rigorous as we would like it to be. Rome wasn't built in a day, so that we don't want to do everything today. We just wanted to, all I wanted to do was just teach you the 4 methods and leave you alone. Just the 4 methods. And so there it is. These are our bread and butter methods. The plug-in method, it's easy. The constants, you get an indeterminate form. The engineer's method, it's very, very intuitive. It's good way to introduce limits. The problem, it's a guess. The rewrite method, very, very nice when you can do it. The problem is sometimes you can't rewrite it. The graphing, very, very intuitive, almost like the engineer's method. The problem is similar. Sometimes it's not a famous graph, so you just end up plotting points like the engineer's method. Anyways, I think I just we talked about these 4. That's good. Sorry, I didn't want to break your heart, but that's it. I know I got a problem.